Welcome to Brain Vision.
Of our question, we're told that the uncertainty in R is equal to the radius R. And we want to use the Heisenberg uncertainty principle, which says the uncertainty in the momentum times the uncertainty in the radius is greater than or equal to h bar over 2 pi. So we can simply solve for the uncertainty in the momentum, delta p, using this. So we find that delta p, just dividing both sides by delta r and then replacing delta r with r, is greater than or equal to h bar divided by 2 times delta r, but again, we're replacing delta r with just r. And we can box that in as our solution for part A. For part B, it says it wants us to find an expression for the kinetic energy, K. Well, kinetic energy is p squared over 2m, and p is equal to 2 times delta p. Since delta p is the uncertainty in p, or plus or minus a value, 2 times that value is going to be our p value. So this is equal to h bar over r. So now we can replace p with h bar over r in our equation for k, and we find that k is equal to h bar squared divided by 2 times the mass of the electron, m sub e, times r squared. We can box that in as our solution for part B. Part C, the energy is equal to K plus U, the potential plus the kinetic. So we'll replace the kinetic with the value we found above and the potential with the value that we're given, which is negative the Coulomb constant times E squared over R. So we have h bar squared divided by 2 times the mass of the electron, m sub e, times r squared, minus k sub e times e squared over r. We can box it in as our solution for part C. In part D, to find an expression for r at the minimum, dE dr is equal to 0. That's the first thing we're going to recognize. So then we can take the derivative of e, the expression we just found above with respect to r, set it equal to 0, and solve for r. If we do that, we find that dE dr, so we'll take the derivative with the first, with respect to r for the first group we come across, which is h bar squared over 2 m sub e r squared. So this gives us h bar squared negative, right, divided by, the 2 goes away because of the derivative, m sub e over r to the third. And then plus, since we're taking the derivative with respect to the second one, the negative sign goes away since r is on the bottom. We get k sub e times e squared over r squared. And then since dE dr is equal to 0, we can set all of this equal to 0. This is r squared. So we can multiply through by the r squared value. And that gets rid of that r squared, and that r cubed goes away, and we're left with just r. So rearranging this to solve for r, we find that r is equal to h bar squared divided by the mass of the electron, m sub e, in units of kilograms, divided by Coulomb's constant, k sub e, times the charge of the electron, e squared. Well, all of these are just constants. You can look them up, but they're all just common constants. Plugging those values in, we find that this is equal to 0.0529 times 10 to the minus 9 meters, or 0.0529 nanometers. You could write it as meters or nanometers. I'm going to write it as nanometers, and we can box that in as the solution for part D. Part E wants us to calculate the value for the energy. So now that we know R, if we go back up here, we have this expression for energy. Everything in this expression is just a constant except for R, but now we know the value of R, so we simply just plug that in and get a value for R energy. Doing that, we find the energy is equal to negative 13.6 eV, electron volts. We can box that in as our solution, for E. If you want to get directly to electron volts, you can use the value for h bar of electron volt seconds. So that's 4.1357 times 10 to the minus 15 electron volt seconds instead of using the joule second version of h bar. Okay, so now on part F, it wants to know if this supports the Bohr's model. Well, to determine whether or not this answer compares with the Bohr's theory, we just need to look at the values for the energy, E, and the value for R. And since R is the same as the Bohr's radius, and you can look that up, but it's the exact same value as the Bohr's radius, and E is the same value as the ground state energy of hydrogen, it does support the Bohr's radius, or the Bohr's theory. Blow this up, make it a little bit bigger, and that is our answer for part F.